Let's continue our discussion of derivative rules without using a limit so that we can apply derivatives more quickly. So in this case, let's look at the derivative of the natural exponential function. So the first thing I'm going to do is I will tell you the rule for differentiating the natural exponential function. Then I'll kind of show you why it is that, and then at the end we'll do some examples applying the rule. So the derivative of the natural exponential function. So that means if we want to differentiate the e to the x function, this is your exponential function that's natural, it's base e. So base e is called natural. Natural logarithm is base e. Natural exponential is base e. So one of the easiest derivatives there is. And in fact, it's why e is so important to us, is because it is its own derivative. So if you differentiate e to the x power, you get e to the x power again, which is really fascinating. And so what this is saying is the slope of the tangent line to the e to the x function. So this is the rule here. Let me kind of put that in a box. That's important. But the idea is if you graph the e to the x function, which looks something like this, then if you want to know, for example, the slope of the tangent, so this is y equals e to the x. Let me write that. Let me label the function y equals e to the x. And you want to know the slope of the tangent line at 2, for example, right? The slope of this tangent line. Well, the slope of this tangent line is the same thing as e to that x power. So in this case, the x value is 2, so the slope is e squared. And that is also the output of the function when x is 2. So the slope of the tangent line on this e to the x function, the rate of change of this function, is always equal to the output or the y value of the function. And this e is the only number with that property. So that's why it's so important to us. That's why we give it the symbol e. Just like pi gets its own name, its own symbol. Okay? So really fascinating stuff with this e character. All right, but let's see why the derivative of e to the x is e to the x. So we know that if we want to differentiate, let's use a different color. If we want to differentiate e to the x, we could do it by looking at a limit. So the derivative with respect to x of e to the x will be the limit as h approaches 0 of f of x plus h, so that's e to the x plus h, minus f of x, well that's e to the x, all over h. And we have to somehow evaluate this limit. Now, this is kind of the cool algebraic part that I'm going to remind you of here that you'll encounter throughout calculus and the rest of your math courses. So just real quick, let's recall that if I want to do something like x squared times x to the 7th, that's the same thing as adding the exponents. Okay? So if x squared times x to the 7th equals x to the 2 plus 7, it's also true that, well, if I have x to the 2 plus 7, that's the same thing as x squared times x to the 7th. It works both ways. So it's true that if you have e to the x plus h, well, that's the same thing as e to the x power times e to the h power. And it's actually pretty obvious if you look at this. Since these have the same base, you would add the exponents to get that. But now we want to split this guy apart going the other way. And that's what we're going to do over here. So this is going to turn into the limit as h approaches 0 of e to the x times e to the h, when I split that apart, minus e to the x all over h. Okay? Now that's a crucial step because now the two terms on top have an e to the x in common. So what we can do, that word common should give you a hint. They have a common factor, in fact. Let's take the common e to the x out. So this turns into, I've got e to the h left here, minus 1 left there, all over h. Okay? So we're getting closer. Now, just so I make sure not to go out of view of the camera here, let's come up here and finish this off. Now, e to the x is independent of h. So what I can do is I can pull my e to the x out to the front of this limit. So this is e to the x times the limit as h goes to 0 of e to the h minus 1 over h. And it just so happens that if you were to try to evaluate this limit, maybe get your calculator out, you could do this, and you approach 0 from the left side and from the right side, so maybe start on the left side, pick numbers really close to 0, plug them in for h into this expression, see what you get, and then plug in numbers really close to 0 on the right side from the positive side for h and see what you get. But what you should see is that the value of this is getting closer and closer to something like 2.718 da 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 da. And in fact, this limit is actually equal to e. Or sorry, I totally blew that. This limit, if you look at it, you should get closer and closer to 1. Okay? So this limit, when you evaluate it, should go to 1. And so that means that you get e to the x for your final answer. Sorry, I threw off the whole progression of this idea by messing that up, but it happens. So the derivative with respect to x of e to the x is e to the x, and it depends on the value of this limit. And the cool algebra that we saw here was doing this splitting of exponents in reverse instead of combining like we're used to here. Okay, so let's try some examples with this function. Maybe we'll just do one, because this one's pretty basic. So let's determine, so we could call this an example if we want to. Let's determine the derivative with respect to x of 3e to the x minus 4e to the x over 5. No, I don't really like that. Let's just do the derivative of 3e to the x, and I'll assume that once you get this, you can look at other types of problems and figure them out. So in this case, what we can do is, because we just have a constant multiple here, I can apply my derivative to the e to the x function. So we just get the derivative with respect to x of 3e to the x. Well, you can push the derivative in, because this is a constant multiple. You can push it past the 3, so you can do 3 times the derivative with respect to x of e to the x. And the derivative of e to the x is just e to the x. So the derivative of 3e to the x is just 3e to the x, because it's just a constant multiple which you can factor out. Now, in practice, typically once you get practice, you don't write this step and you just skip down here, because you know you can push the derivative in past the constant coefficient.